Yeah, good evening all. Yeah, so today we are going to discuss about the organic photochemistry. This is your block 3. Okay, so the organic photochemistry. So generally, it deals with the organic reactions which are takes place with help of the photo light or the photo energy here. Okay, so generally the few of the reactions. Okay, so few of the reactions which are not feasible to conduct the thermal reactions, right? So few of the reactions which are not feasible for the thermal reactions can be carried out by the these photochemical reactions here, photo energy, right? So this is a very important topic here. Okay, and it is very interesting topic and it is very important, right? Yeah, so here before going to that photochemistry, okay, so first you have to know the transitions here, electronic transitions, right? So generally any of the reactions, okay, so any chemical reactions which are takes place due to the excitement of the electrons here, right? The excitement of the electron from ground state to excited higher energy level, lower energy level, or the ground state energy level to the higher energy level here. Okay. So generally that promotion we call that is a promotion of electron. Okay. So that promotion of electron is called the electronic transition here, right? So the promotion of electron is called the electronic transitions. Okay. So yeah, is it audible, ma?
Yes, sir.
Yeah, fine. Right. So here the promotion of electron from lower energy level to the higher energy level is called the electronic transitions. And these electronic transitions are various types depending on the depending on the electron on which state is going to occupy, right? So depending on that, we are classifying these transitions into various types like sigma to sigma transition here. Okay, and pi to pi star transition, sigma to sigma star transition, and n to pi star transition here. Okay, and so these are the various types of transitions, electronic transitions here. Okay, the possible means here where the right. So for example, here the sigma, right? Sigma, it is a ground state energy level. Okay, and sigma star, it is higher energy level here. Okay, exit state energy level. Yeah, right. So here, right. So here, for example, just to assume, right. So these are the various energy levels here. Okay. So like, okay. So this is the sigma here. Okay, and this is your okay, sigma star, right? So here the star indicates, right, the exit state here. So the higher energy level. For example, one electron is there. Here the two electrons are there. This is one electron here. This is one another electron, right? So this is ground state level here, right? So this is your lower energy level or the ground state. Just to assume this is the ground state here. Okay, and upon gaining electron, right, upon supplying some photo energy here, right? So where we are supplying the energy here, right? So that is a photo energy or the thermal energy generally, right? So by utilizing this particular energy here, right? So H nu E, it is energy E. Okay, so this is energy here. So some amount of energy is supplied to that particular system, right? That particular electronic system. Then the promotion of electron from ground state to excited state will be takes place. Okay, so this is lower energy level and this is higher energy level. Okay, so then what you get? So this electronic system rearranged like this here. Okay, so this electronic system rearranged like this means here the sigma, okay, and this is your sigma star. Okay, or pi, you can take sigma the pi whatever. Okay, so this is the star here, right? So here now after excitement, right, or after gaining the energy, so the system is undergoes the rearrangement. Okay, so the electron system is it, you can see means one electron gets promoted from the lower energy level or the ground state level to the higher energy level. Now you see sigma, it is having one electron, sigma star having one electron here, right? So this is your exit state level. Okay, so and this sigma, this is called the, okay, yeah, so this is called the bonding molecular orbital, right? So this is BO, we call this is the BMO. Okay, this is called the BMO. BMO means bonding molecular orbital, and this sigma star or the pi star, whatever, right? So this is called the ABMO. Okay, AB, right? So this is called the AB1, means anti-bonding molecular orbital. Yeah, the bonding molecular orbital and anti-bonding molecular orbital. Okay, so where the bonding molecular orbital is the lower energy orbitals and anti-bonding molecular orbitals are the higher energy orbitals here, right? So during the transition, right, the during the transition where the promotion of electron from bonding molecular orbital to anti-bonding molecular orbital will be takes place. Okay, so right, yeah. So now you see, yeah, electronic transitions here. So you can see here. Okay. So generally we have various electronic transitions here: sigma to sigma star, pi to pi star, and n means non-bonding here. N to pi, right? Sigma star and n to pi star. So these are the some various possible transitions in the organic molecules here, depending on the type of bond or the bonding electrons present in that particular system or the compound or the group here. Okay, right. Here, simply you take the alkane. When you take the alkane here, so generally alkane consists only the sigma electrons, right? So you can have only the sigma to sigma star transitions. You cannot find the pi to pi star transition, n to pi star transition, because there is no pi bond, there is no sigma bond here. Sorry, there is no pi bond and there is no n bond. So you have only the sigma. Okay, so here by applying of, when you apply this 154 nanometer wavelength of, right, so wavelength here, then this one of the electron from the ground state gets promoted to the excited state or the higher energy level sigma star here, right? So like that, this is your ground state level, and by utilizing this 154 nanometer, right, wavelength here, radiation, that particular 154 nanometer radiation, it is going to excite it to the higher energy level, this one. Okay, yeah. And here generally in the photochemistry we use the, right, will use UV visible range of the radiation. Okay, so what is the UV visible range of the radiation here? So 200 to, right, 200 to 400 is the what is that UV range of the radiation, and 400 to 800 is the visible range of the radiation there. Okay, so that much energy or that much radiation is enough for this electronic transitions here, right? Okay. Yeah. So now coming to this carbonyl chromophore, right? So generally in the carbonyl chromophore, so carbonyl compound are having all kinds of electrons here, right? The carbonyl compounds are having all kinds of electrons like sigma electrons, pi electrons, and non-bonding electrons. Okay. So if you see the carbonyl compound here, for example, okay. So this is your carbonyl compound, CO, carbonyl, right? So whether it is aldehyde or the ketone or the acid, okay, ester, amide. So all these are carbonyl, all they are consisting the carbonyl functional group here. Okay, so where it is having this, right? So this is sigma, okay, and this is your pi, pi electrons here, sigma electrons here. Okay, and these are the non-bonding electrons, n electrons. Okay, n electrons. So carbonyl group is the best example to explain all the transitions. Means in the carbonyl compound, all the transitions are possible here because it consists all type of electrons here, right? Okay. So and yeah, chromophore, carbonyl chromophore. So in the UV visible spectroscopy, we know that, right? You are coming across in the first year practicals here. What is mean by chromophore? Right. So here the chromophore which absorbs the UV visible range of the radiation is a chromophore here. Okay. So in this particular carbonyl chromophore, you can see the three types of transitions here. Three types of transitions are possible because all kinds of electrons are present here. And if you see the structure of this carbonyl compound, you can see this is the structure of the carbonyl compound here. Okay. So where this particular, right? So in the carbonyl group, right? Yeah, the carbon is having the sp2 hybridization here, and the oxygen is having the sp hybridized oxygen here. Okay, and if you see the structure of this particular carbonyl group, okay, the carbonyl group here, right? So where the p orbital of the carbon, right? So this is your carbon here, and the p orbital of this carbon and the p orbital of the oxygen. This is oxygen here, right? You can see here is a carbon. This is a carbon here, and this is your oxygen. So this is a p orbital. Okay, so the p orbital of this carbon and the p orbital of this oxygen both are okay, right? How they are aligned here, how they are oriented, right? So both are parallel to each other. Okay, so the p orbital of the carbon and p orbital of the oxygen both are parallel to each other. So they can, right? So they can undergo see, right? Side to side overlapping here. You can see, right? Side to side overlapping here. So side to side overlapping resulting formation of the pi bond, isn't it? Yeah, the side to side overlapping resulting in the formation of pi bond here. And you see one of the lobe, right? One of the lobe of p orbital here of carbon and the p orbital, one of the lobe of the oxygen, both are right. So perpendicular to each other, right? Both are, these are parallel to each other and these are perpendicular to each other. So these two undergoes the okay end-to-end overlapping. These orbitals undergoes the side-to-side overlapping, and these two undergoing the end-to-end overlapping, and the end-to-end overlapping results in the formation of sigma bond. Here you can see, right? So this is forming the sigma bond, and the side-to-side overlapping, okay, or the partial overlapping here, they results in the formation of pi bond, and the side-to-side end-to-end overlapping results in the formation of sigma bond. Right. So like that, these orbital lobes are right feasible for the formation of the various sigma and pi bonds here. And these non-bonding electrons, right? Non-bonding electrons here. Okay. So these two pairs of non-bonding electrons are not lies in the plane. Okay, these are not lies, they are not located in that particular plane, means they are not convenient for the overlapping because they are somewhat some degree of deviation is there, isn't it? They are not perpendicular and they are not parallel here, right? So both pair of electrons containing orbitals are unable to form the bonding with these particular carbon and oxygen here. So they won't participate in the hybridization. That's why this particular structure of carbonyl can be written like this here, right? So these two pair of electrons are remained as a non-bonding electrons here. These are the non-bonding electrons because they are not convenient, they are not feasible for the participate in that particular overlapping or the hybridization here, right? So these orbitals are able to undergoes a overlapping and they will form their respective bonds like sigma and pi bonds here. Okay, so like that, here you can see the various types of electrons like sigma electrons, pi electrons, and non-bonding electrons. So it is able to form, able to see the various transitions like sigma, pi, and n non-bonding transitions here. Okay. Okay, right. So you can see the various transitions, right, possible in the carbonyl compounds. Here, in this particular carbonyl compound, right. So already we have seen that in the outermost shell, that is called the valence. Okay, in the valence shell, there are 4 electrons are there, isn't it? It is a 2 pi electrons here, 2 non-bonding electrons here, right? So in the ground state electronic configuration, when you write the ground state electronic configuration, that particular compound, carbonyl compound, is having this kind of right electronic configuration here. And then what we are doing, we are applying some photo energy, some amount of photo energy here. Then the electron promotion will be takes place, and depending on that particular radiation, right? Depending on the amount of radiation, so you can observe the two kinds of excitements here, two kinds of transition. Excitement in the sense the transition, right? So with when you apply the 185 nanometer, right? 185 nanometer radiation, right? 185 nanometer radiation, then you will get the right. So more excited, right? So higher energy excitement will be takes place, and in the 270 nanometer radiation, right? The lower energy transition will be takes place, right? So here generally the wavelength is inversely proportional to the energy, isn't it? Here the lambda is okay. So here the lambda. So, okay. So here the wavelength means lambda. The symbol, the notation for the wavelength is a lambda here. Lambda is inversely proportional to the energy, isn't it? Yeah. So if lambda increases, the energy will be decreased. If lambda decreases, the energy will be increases, right? So here 185 nanometer means lower delta, lower lambda means higher energy, isn't it? This is higher energy transition. This is lower energy transition. Lower energy transition, higher radiation transition, isn't it? Because it is, this is the relation between the lambda and the energy. Okay, so here the this is your higher energy transition here. So at higher energy transition or the lower radiation transition, where the ground state electron, okay, the ground state electron crossing the non-bonding stage, and it gets promoted to the pi star here, right? Here, what is happening here? The ground state, the lower, highest to lower energy level electron is directly promoted to the higher energy, right? Highest energy level here, right? So it is crossing the non-bonding electron. Means this electron are not promoting, only 5 electrons. Okay, 5 bonding electrons are promoting here because the energy is more. Okay, we are applying the more energy. That's why you can see this transition here, this promotion. And in the lower energy level or the higher wavelength, or you can say it is what is that radiation. Okay, so because it is lower energy level, so only the non-bonding electron is gets promoted, right? So the pi electron is not promoting to pi star here, right? So here only the non-bonding electron. So this is okay. So this transition is pi to pi star transition. Okay, this is pi to okay. So here this is pi to pi star transition. Okay, because the pi, okay, this electron is getting promoted to the pi star. Okay, directly by ignoring this one, means this electron are not promoting here, this electron, that's why it is pi to pi star transition. And here what you observe, only this electron, right? So in the higher energy, this is higher energy, sorry, lower energy here, this is higher energy. So here only pi electron, okay, here this electron is promoting here. Okay, this electron is promoting. So this electron is not promoting, this electron is promoting. Here two electrons are there now, right? This one. So here this two, here two. So this electron is promoting here in the, okay, so here. And here this electron is promoting. Okay. So it becomes N to pi star transition. Okay, N to pi star transition. Okay. So generally in the organic compounds, right? So these are the forbidden transitions here. N to pi star transitions are forbidden transitions, means least preferable. And the pi to pi star transitions are very common. These transitions are very common here. Okay. Right. Now the singlet and triplet states here. So what is mean by singlet and triplet states? So singlet state means where, okay, so the two electrons are present in the, right, same orbital. Okay, so in the, you see, for example, this orbital is here, right? So if two electrons are, okay, two electrons are present in the same lobe. Okay, so it is singlet. This is singlet here, right? If it is, okay, so for example, just two electrons are present in the different orbitals. Okay, now it is triplet. This is triplet here, right? Why it is singlet, why it is triplet here? So to calculate the multiplicity, right? To calculate the multiplicity is denoted with the J here. Okay, and to calculate this J value or the multiplicity, this is the formula. Okay, this is the formula. To S means spin state of the, okay, the spin state of the electron here. Spin state means either aligned direction or the anti-aligned direction here. Parallel direction or the anti-parallel direction here. Okay, and plus one. Okay, so for example here, the spin value of this this electron is, for example, this is the upwards. Upwards means plus half, isn't it? The spin values are plus half and minus half. So here is a plus half here, and for this is the downward direction, so it is minus half. So plus half and minus half gets cancelled here, and the value is 0. So 2 into 0 plus 1, so it is 1. Okay, it is 1. So here you see. So it is singlet. And if you calculate the multiplicity for this triplet here, okay, so this is upward direction, either upward or the downward, whatever, right? So, but the condition is in the triplet state, the two electron must be in the different orbitals. Here, the two electrons are in the same orbitals here. Here, the plus half and plus half, right? Plus half is 1. So 2 into 1, 2 plus 1, that is 3. If it is minus half, for example, if downward direction here, right? So the electron orientation is downwards, then minus half, minus plus, isn't it? So it is 1. So 2, again it is 2 into 1 plus 1, that is triplet. Okay, so like that, depending on the, based on that, the orientation of the and the location of that particular electron, we are right. So we are classified two types of orientations like triplet state and the singlet state here, right? And generally triplet state and singlet state, among these two, the triplet state is the more stable, right? More stable state here. Okay, and the singlet state is a less stable state because in the triplet state you can see, right? So in the triplet state, the two electrons are present in the, right? So in the different orbitals, okay, the two electrons are present in the different orbitals. So you can see there is no repulsion if the two electrons are, right? The two electrons are what is that? Adjacent, right? Or two electrons are in the same orbital here, then they may undergo see repulsion here, right? And the two electrons are here. So both are repulsive in nature. Right? If both electrons are in the different orbitals, then there is no repulsion, there is no collision between the electrons. So they will be the more stable here. That's why the triplets, right? The triplet energy state is a more stable than the singlet energy state here. Okay, right. Right. So here you see how the electronic transitions are takes place when you apply some amount of photo energy. Right. You can see here is a two electrons are there in the S0. S0 means a singlet ground state level. Right. S0. Sorry, it is zero. It is zero ground state level here. Right. So in the zero ground state level, in the bonding molecular orbital, there are two electrons are there. Okay, and the anti-bonding orbital, molecular orbital level is empty, right? Okay, this is empty. Generally, we call this is HOMO. Okay, so BMO is called the HOMO. Okay, this is called HOMO. So it will come in the pericyclic actually, HOMO. Okay, so this is called LUMO. Okay, LUMO. LUMO. LUMO means lowest unoccupied molecular orbital. Right? So least or the lowest unoccupied molecular orbital. HOMO means highest occupied molecular orbital here. So two electrons are there. So it is highest occupied molecular orbital. So with help of this H nu, the energy, right? So these electron, one of the electron is going to promote it from HOMO to LUMO, right? HOMO to LUMO or BMO to ABMO, antibody molecular orbital, right? And with their spin inversion, right? So that is depending on the energy applied. Okay. So for example, right? So here you see when this particular H nu, right? So when this H nu is right, so energy is more, for example, right? So you can see this particular, right? So this electron is directly promoted to the antibody molecular orbital. Okay, and here is the with inversion of the spin here. Here there is no inversion here, isn't it? There is no inversion in the spin state. Here the inversion of spin state will be takes place here, right? The first excited triplet state. First excited triplet state. Generally, the triplet state is the lowest energy level because this is the stable state, isn't it? It is a stable state. So the energy will be the less, right? The energy will be the less here. And this is the singlet state, more energy level state here. And the singlet state is, there is no inversion of the spin. Okay. There is no inversion of the spin because the electron is promoting as usual, means without inversion of the spin here. And in the first excited state of triplet state, in the T1, here is a S1, right? First excited state of the singlet state, no inversion of the spin. And in the triplet state, you can see the inversion of the spin state of the electron here, right? So these are the two changes during the excitement here. You can see the two changes here. And this means the transitions are takes place depending on the energy applied, right? Or the supplied. The energy, how much energy you are applying or the supplying. So based on that, these kind of promotions or these kind of transitions are possible, and you can see that. Okay, right. And generally, the energy, right? So in the energy point of view, the S1, right? The singlet state energy is more than the triplet state energy, right? Okay. And now you see this promotion of the electron from the non-bonding and the pi electron. Means if you take the example of the carbonyl compound, right? The carbonyl compound here. So here we are applying the 270 nanometer radiation, right? So then here the N to pi star transition is takes place because 270 nanometer means, right? How much it is? It is low energy, isn't it? Because the higher wavelength is a low energy. So when you apply 270 nanometer radiation, so only the non-bonding electrons gets promoted here. If you apply 153 nanometer radiation, then pi bond electrons gets promoted, right? So here you can see the non-bonding electron promotion from non-bonding to pi star transition with their retention of spin or the inversion of the spin, right? You can see there are two possibilities here. Okay, the two possibilities here. This particular, right? At a higher energy level.
Hospital case follow. Sai bye.
You see, higher energy level, there is no inversion of the spin, and here you can see, right, in the triplet state where the inversion of the spin is takes place from non-bonding energy level here, right? From the non-bonding energy level, the electron promotion is takes with the inversion of the spin here, isn't it? Because the direction of electron is going to change. Okay, the direction of electron is going to change here. So it is with inversion of spin, and here the retention of spin here, the retention of spin state, and the energy always the the singlet energy of the N to pi star transition is more than the triplet here, because the triplet means it is always low energy, right? The triplet energy level always the low energy level here than the singlet energy level. Okay, so here also this is the N to pi star transition here. Now the pi to pi star transition. Okay, so at 185, right? So I told the 153, not it is not 153, it is 185, right? So at 185 nanometer, right? So here also you can see the two kinds of transitions here. Okay, one is the higher singlet energy level transition and the highest triplet energy level transition with the retention of spin state and inversion of spin here. Okay, so here you see in the singlet energy level, you can see the transition of the electron or the promotion of the electron with the retention of its spin. Okay, no change in the spin here, right? So, and here you see with the inversion of spin. Okay, and the energy is, you can see this energy, right? So always the triplet energy level of the pi to pi star transition is more than the singlet, is less than the singlet. Okay, right? Like deactivation of excited state here. Okay, so in above we discussed that when we apply a amount of radiation or the energy, the electron is going to excited and the electron is going to promoted from the ground level energy level to the excited state or the higher energy level here. Okay, so after excitement, the electron need to come back into the ground state level, right? Okay, so after excitement, right? So by that particular electron is again it come back to the ground state energy level. Then only that particular compound or the electron becomes stable. Otherwise, it remains unstable only, right? But we need to stabilize that compound right? So to get the stability, that electron must return to the ground state energy level. Okay, and that particular generally that returning to the ground state level is called a deactivation, right? The deactivation. So this deactivation is various types, right? The deactivation is various types here, and this deactivation is explained by the Jablonski diagram, right? So this is very good and right. So this is a very important and good diagram. Jablonski diagram is it explains, right? It explains the deactivation of the excited state here. Okay. So Jablonski diagram is important in the examination. So they will ask for the 4 marks in the exam, right? So always it is repeating question. Jablonski, describe the Jablonski diagram. So it is very important topic here. Okay, deactivation of excited state is very, very important. Okay, fine. So in this means deactivation of the excited state, so you can see the various stages, right? So various stages here. One is vibrational cascade, and that is VC, internal conversion IC, intersystem processing ISC, phosphorescence, and the fluorescence, right? So generally, when that particular electron gets promoted here, after a reasonable time, that electron again it come back to the ground state level, right? And when it is coming back to the ground state level, so it may emit the energy or it may absorb the energy, right? So it may absorb the energy or it may release the energy here, right? So depending on that, we are having these phenomena here: vibrational cascade, VC, IC, and ISC, and phosphorescence and fluorescence. So this terminology is very, very important. Okay, these terminologies: VC, IC, ISC, fluorescence, and phosphorescence. These terminologies are very, very important here. Since they will ask the definitions of this. Okay, and what is VC and what is so all these definitions we'll see here. And yeah, right. So vibrational cascade. Okay, so when that particular electron is returning to the ground state here, so how the fate of that electron, right? When it is returning to the ground state, so the fate of the electron is, you can see here, upon absorption of radiation, the molecule may be excited to Vx level of S2 state, right? So here you see Vx of S2 state. Vx means the high vibrational level, right? Higher vibrational level of that particular energy state to the higher electronic, right? Electronic level of the that particular state here. Vx means a vibrational, S means a spin state. Okay. So vibration, generally when that particular electron absorbs the energy, okay, so that energy brings the changes in the various types of energies, because the energy is not a, it is a single phenomenon. Energy is a, okay, the total energy, generally the total energy here, T means total energy. So total energy is a combination of, right, it is a combination of VE here, okay, and IE, so, okay, RE, rotational energy, vibrational energy, rotational energy, right, and E, electronic energy, right? So vibrational energy, rotational energy, electronic energy. So this combination of these three is equal to the total energy, right? So vibrational means this vibration energies leads to the vibration of the molecule. Vibration means the shaking, right? Or the vibration, like, okay, so some movement. And rotation. Rotation means the rotation around that bond, right? Rotation around that bond here. In the rotational spectra, V means vibrational spectra, like electron, right? and E means electronic energy. Electronic energy means the promotion of electrons, right? So like that. So okay. So here the vibrational, higher vibrational level of the, right? These vibration levels are various types, like V0, that is the ground state vibrational level, V1, first vibration level, V2, second vibration level, V3, like that. Vx means the, it is n number of, okay, the highest. Vx means the highest of level of the vibration level, Vx of S2, right? So it is not changing. Okay, S2 means the higher spin state, right? It is not S, not S1, S2. S2 means a higher spin state of electronic state to V naught of S2. Okay, V naught of S2. So just you observe what is happening here, right? So when the electron is returning, so the spin is not changing, right? The retention of spin is takes place, right? So there is no change in the spin state. Only it is changing the vibrational energy level. Okay, Vx to V naught. V naught is a ground state. Vx is the highest energy vibrational level here, right? So the retention of spin state is takes place here, right? So the okay, so that's why we call this is the vibrational cascade, right? Vibrational cascade means the when that particular deactivation or the de-excitement is takes place with from Vx highest vibrational energy level to, right, ground state vibrational energy level with the retention of spin state is called the vibrational cascade. Okay, right. Next, internal cross conversion, IC. IC. So here the IC means here V naught of S2 state to Vx of S1. So it involves the changing of vibrational level as well as the spin state. So the inversion of spin is taking place, isn't it? The spin multiplicity, the inversion or the spin multiplicity is changing. Here the S2 becoming S1. Okay, S2 become S1. V naught become Vx. Okay, so what is happening here? V naught ground state. Okay, so ground state means vibrational energy level to higher vibration level, right? And spin state is S2 to S1. So the changing in the multiplicity, right? Sorry, it is changing in the, right, changing in the spin level, but multiplicity is retained. Sorry, yeah, right. So multiplicity is retained because singlet to singlet. Okay, singlet to singlet means no change. Retention of the multiplicity here. Retention of the multiplicity here also retention of the, okay, in the vibrational cascade also retention of multiplicity, and the electron promotes, right? Here the Vx to V naught here, but here V naught to Vx, right? Higher vibrational energy level to, okay, lower energy vibration level to higher vibration level, and S2 to S1. So the spin retention is takes place because singlet becomes singlet only, no triplets. Okay. So in the vibrational cascade, no change in the spin multiplicity, and in the IC also no change in the spin multiplicity. Next, intersystem crossing, ISC. Okay, ISC. It is very, very important, right, phenomena in this de-excitation or the deactivation here. Okay, fine. You see, this involves a V naught of S1 state to Vx of T1. So what do you observe here? So the vibrational energy level is changing as well as the spin state also changing, spin multiplicity, right? The spin multiplicity also changing here, right? So first to singlet, okay, first to singlet state of the electron becoming the first to spin state of the triplet. Okay, S1 to T1, V0 to Vx here. So both will be changing vibrational level as well as the, right, spin multiplicity also changing here, right? Or V0 of T1 to Vx of S0. So both changes here. So this is called the inter-system crossing. And the fluorescence. Fluorescence generally it is the emission of radiation from the excited state to give the lower state in the multiplicity. Okay. So here what is happening in the fluorescence? Where the emission of radiation, where the energy is released here. Emission of radiation means the energy is released. Right? So during that returning of the electron from S1 to S0, right? With the release of some amount of energy here. That is the fluorescence. Okay, fluorescence means S0, S1 to S0. So here there is no change in the spin multiplicity, right? Without spin multiplicity here. Okay, fluorescence. And the phosphorescence, emission of radiation from an excited state to give a lower state with change in the multiplicity, right? So here also the energy release takes place in both cases, phosphorescence and fluorescence. In both cases, the energy is released here, right? Right? The emission of energy means the release of the energy takes place, but in the fluorescence, there is no change in the spin multiplicity. In the phosphorescence, you can see the change in the spin multiplicity. Here, the triplet to singlet, right? Triplet to singlet. Spin multiplicity takes place here. And all these phenomenons, right? All these terminologies like vibrational cascade, inter-system crossing, okay, and internal conversion, phosphorescence and fluorescence. All these are explained in this diagram. This is called the Jablonski diagram here. Jablonski diagram. Here S0, here the S1. Higher, okay, higher singlet energy level here. And here is a T1, T0 to T1, T0 to T1 here. Generally, triplet is lower energy here, singlet is a higher energy here, right? And here you see B is a VC. Where is the B here? You see, here is a B. So Vx to V0. Vx is a higher vibration level, V0 is a lower vibration level, right? So this the returning when the returning the electron here, right? So it is coming from Vx to V0, okay, and ISC, inter-system crossing. See here, you see V0 to, right? So here the V0 to here, you see, yes, right? So here the V0, it is changing, right? So S1, right? Here the S1 to T1, right? So what is the IS here? You see here, inter-system V0 to Vx, okay? So here the V0 of S1, okay, V0 of S1 to V1 of T1, right? So this is your ISC. So what is ISC here? Right? What is ISC? V0 of S1. Okay. V0 of V0 of S1 to, right? So V1 of T1. V1 of T1. Or the Vx. You say it is Vx, right? Because right? So Vx of okay. So here the Vx of T1. Okay. So here this is V naught of T naught here. Okay, V naught of T naught. Okay, fine. So it is a V T1 of Vx something, right? It may be X or 1 or 2, whatever, right? So you see, this is the ISC. It is inter-system crossing. Inter-system means yeah, the singlet to triplet, isn't it? Yeah, this is the singlet system here, and this is your triplet system, isn't it? This is singlet system, this is triplet system. So inter-system crossing. Inter means different. So it is crossing the inter-system, singlet to triplet. That's why it is ISC. Okay, so this is important. Yeah. The transition is important, right? So all these ISC, VC, IC, phosphorescence and fluorescence, all these are explained in this Jablonski diagram here. Okay. So phosphorescence or the fluorescence. You see the fluorescence here, G. So fluorescence is a here S1 to S0, right? S1 to S0 here, this one. Right. So S1 to S0. This is your fluorescence. Okay. Fluorescence means there is no change in the spin. S1, yes, singlet, singlet. And phosphorescence. Phosphorescence is the right. So phosphorescence. What is phosphorescence? Yes, yep. You see this here. Right. So written. Right. So T1 to S0 here. T1 to S0. Right. T1 to S0 here. So it is change in the inversion in the spin state. Okay. So this Jablonski diagram is very, very important here. It's an intersystem crossing in the efficacy. Generally, ISC, right? Here the ISC generally it is forbidden process in the organic compounds here, right? Because intersystem crossing, right? So it is takes more energy here to cross this system. So it takes more energy. Okay, that's why in most of the compounds it is forbidden process here, right? But if it's right, if energy gap between the energy gap between the two levels is less, then this ISC will be possible here. Okay, so here in this particular compound, you see here the right. So here this S1 level is at 74 energy level, and T1 is a 69, right? So the difference between the difference between S1 to T1 is a how much it is 5, right? The energy gap is a 5 here. So the ISC is possible for this compound, isn't it? This is the example for the benzophenone. Okay, this is for the benzophenone. Okay, there is a pH. Right? So for benzophenone, right, the energy gap between the singlet state to triplet state is less, right? So here you see this is the 74 kilocalorie per mole is the singlet energy level here, and 69 is the triplet energy level, and the difference will be the 5, isn't it? 5 kilocalorie. 5 kilocalories. So it is less negligible amount, less amount here. So ISC will be possible, right? So if energy level, right, the energy gap between the S1 to T1 is less, then ISC will be possible here. Okay. And if it is more, then ISC will not be possible. For example, if you take the butadiene, right? So for this butadiene, okay. So for this butadiene, okay, S1 energy level is 124 here. For S1, it is 124. For T1, it is 60. So difference, how much it is? 64 difference is there, right? So the difference is a 64. So very large difference, right? So the energy gap between these two is more. So the in the butadiene, ISC is not possible. Yeah, the ISC is not possible here. Okay, ISC is forbidden. If it is less, then it will be possible. Okay. And it will be possible by doing the photosensitization, right? So the photosensitization, another triplet energy transfer. Okay, because you see For benzophenone, the energy gap between the triplet to singlet is less, isn't it? It is simplified. And for this butadiene, the energy gap between S1 to T1 is the 64. Difference is there, right? So for benzophenone, ISC is possible. Inter-system crossing is possible. And for this butadiene, the ISC will not be possible here, right? And this will be possible when we treat this particular, right, benzophenone with butadiene or the butadiene with benzophenone. Then the energy transfer will be takes place from this benzophenone to butadiene. Then it will be ISC enabled. ISC can be enabled by transferring the triplet energy from donor to acceptor. Generally, this benzophenone acts as a donor, butadiene acts as a acceptor here. Okay, that is called the photosensitization. Right? Photosensitization means with the means the transfer of the energy in between the two. Okay, the two kind of compounds. One compound is with ISC, another compound is without ISC. For these kind of compounds, the photosensitization can be takes place here. You see, here the D is a donor like benzophenone. Okay, so the D by absorbing the energy, so it undergoes the singlet state of your D1 here. Right? Now this D1 by ISC, it is going to convert into triplet state of the donor, right? Triplet state of the donor, excited state here, triplet excited state of the donor. Now we are adding this acceptor like butadiene to this triplet, right? The triplet state of the donor. We are adding the A means acceptor like butadiene, which is having the 0 ISC value or less ISC or the negligible ISC value here, right? Then what is happening here? This triplet energy is transferred from donor to acceptor here, right? Donor to acceptor. So this kind of transfer of the triplet energy from donor to acceptor is called the pinching of the molecule. Pinching, okay, pinching. Right? Here you see, right? This is the benzophenone. S naught means a singlet ground state level here, right? By absorbing the energy, it is going to right. So it is going to exit state here, N to pi star transition, and this singlet state. Okay, this is the singlet state. It is going to convert into triplet state by ISC. Okay, by ISC here, and now we are transferring this triplet energy of the benzophenone or the donor to this butadiene, which is not having the ISC value here. Now this becomes the right. So this benzophenone is become 0 ISC value, and butadiene it is gaining the triplet sensitized energy. Right. So this mechanism is called the pinching mechanism. Okay, the pinching. Yeah, this one, the pinching mechanism. Okay. Here you see, this is the conversion of this pinching or the triplet sensitization of the molecule. Right, you can see. Right, so here you see the some difference. Right, so here the biacetyl group is there. Okay, biacetyl group, and the pyrene and the naphthalene. Right, so the comparison. Okay, the comparison. So now you see, right? So biacetyl here, this is your donor, for example, right? The biacetyl is a donor compound here, and the pyrene and the naphthalene, these two are acceptors here. Okay, these two are the acceptors, and biacetyl is the donor here. Okay, now whose energy gap is less? Right? For example, in the pyrene, if you take the pyrene, you see this is the energy gap of this here, right? S naught to T1 here. S naught to T1. One second, I will show you. Okay, here the this much energy gap is there. And in the naphthalene, okay, so this much energy gap is there. Okay, so for example, its values, for example, it is 2, its value is 4, isn't it? Because a much energy gap is there in the naphthalene. So now, right, this pyrene is having the less energy gap, naphthalene having the more energy gap. So the acetyl, this is the donor here. Acetyl is a donor. Okay, acetyl is a good donor, and pyrene and the naphthalene is the acceptors here. These are the acceptors. Both are compete, right? Both are compete each other here. So the donor, right? Among these pyrene and naphthalene, which molecule is eligible to transfer the triplet energy of the donor here? Pyrene, because its energy gap is less. Because for the ISC, okay, for the ISC, the main criteria is the energy gap must be less. The energy gap must be less here. Okay, so this biasteal can be transferred the triplet energy here to pyrene, but this is not takes place here. This is forbidden. This is not allowed. This is allowed here, right? Because it is having less energy gap. Okay, so these are configurations, means who's right in the carbonyl compound. So in the triplet state and singlet states, which is more stable and which is more energetic. So you can see all this. Already we discussed these things, right? Here you see the energy gap between these is more, isn't it? And here the energy gap is less here. So generally this is more stable, isn't it? Because this is a less energy gap, so it is more stable here. Right. Next, reactivity of excited states here. Okay. So generally in the carbonyl compound, the carbonyl compounds, actually this lone pair electron, right? The n bond electrons are not parallel or the perpendicular. Either it is not parallel and not perpendicular to the what is that? P orbital of the carbon here. So they're unable to form the bonding with this one. They're unable to form the bonding here. But upon the tilting of the molecule, right? Tilting or the some rotation of that particular bond here, so it is able to form the bonding. Okay. So that is takes place in means by what is it? Applying some energy, some amount of energy here. Okay, other radiation. Okay. So now the photochemistry of carbonyl compound, right? So very important. So generally the carbonyl compounds, okay. So the carbonyl compounds undergoes the three types of photochemical reactions here. One is a photoreduction, okay, photoreduction and pattern of Gucci reduction and Norris type of cleavages here. Right? So photoreduction, pattern of Gucci reaction here, and Norris type of cleavages. So very important. Right. Yeah, so there is not much time here, so we will discuss, right, in the next class.
Sir, excuse me, sir.
Yeah, tell me.
The page number 1, exacted UES is there, sir. What is the UES abbreviation? 141.
No, 141.
UES, excited state, ground state on the UES is there, sir. Right, 141.
141.
Sir. Last, sir. Last, sir. UES of cyclohexadiene, sir.
141.
141.
So actually the page starts from 196 కదా 141 ఎక్కడ నుంచి వచ్చింది
ఇక్కడ సహా ఇది సార్ ఇదే సార్ సిలబస్ ఈరోజు లేదా సార్ ఈ సెకండ్ చాప్టర్ సార్ అది యూనిట్ 2 గ్రౌండ్ స్టేట్ ఎలక్ట్రాన్ గ్రౌండ్ స్టేట్ అండర్స్టాండ్ సార్ జిఎస్ యూఈఎస్ఏ అర్థం కాలేదు
పేజ్ నెంబర్ చెప్పు కరెక్ట్ గా
Sir, pick pet. Lesson chapter, sir. 141. Electrocyclic reactions, sir. Unit 8, page number 141.
Electrocyclic reaction. Pericyclic reaction. నువ్వు చెప్పేది?
Sir.
ఇక్కడ లేదు.
Okay.
141.
141, sir.
ఏమున్నది?
UES ఉంది సార్. GS మీన్స్ గ్రౌండ్ స్టేట్ అనుకుంటున్నా సార్. మెయిన్ది లాస్ట్ లో సార్ GS ఆఫ్ ఎగ్జాట్రైన్, UES ఆఫ్ సైక్లోహెక్సాడైన్.
షేర్ చేసి ఆప్షన్ ఉంటే చేయగలుగుతావా?
మంచి సార్, చేస్తా సార్.
అంటే మీన్స్ ఇలా ఇప్పుడు స్క్రీన్ మీద
ఒక్కసారి ఏమన్నా సార్ నేను మీ వాట్సాప్ పెడతలేదు సార్, నాకు రావట్లేదు సార్, దీని నుంచి ఐడియా లేదు.
It is upper excited state.
అప్పర్ మేడం,
Upper excited state.
ఓకే మేడం, అప్పర్, అదొక డౌట్. ఓకే మేడం, థ్యాంక్ యూ.
ఓకే,
థ్యాంక్ యూ సార్.
share in the WhatsApp, then I will clarify your doubt. Okay, so tomorrow the next class, I think it is on Sunday, so we discuss the photochemistry of carbonyl compound. So I'm stopping here.